Thank you very much. It's great to be here. I'm going to talk a little bit about the benefit for utilities of artificial intelligence as well as the utilities customers. And let me see if this is a button. This is the button. Yes. What you see here is in February 2021. It's actually my daughter. And you may not be overly impressed if you live in Canada about somebody being this excited about snow. I grew up in Germany. I wasn't this excited about snow. My daughter is still growing up in Texas, and so snow is a somewhat more unusual phenomenon for her. So on this February night, super excited, she knew next day school is going to be canceled because if there's snow, there is no school in Texas. However, this moment over the next few days turned into what was somewhat of a disaster. In 2021, I don't know if this was also news in Canada, we had Winter Storm Uri, which turned into essentially all of Texas was in freezing temperature. We had about negative 12 degrees centigrade or so where I lived. Again, very unusual. So not just school that stopped, but energy stopped also flowing. Several days of outages, and you see all of these headlines that followed about millions of people without power. Water lines broke. Actually, over 250 people died from this disaster as well. And it was a very expensive undertaking. Now you can say, well, that's not what typically happens, and you're right. But there's so many different types of major events that happen actually also here in Canada, that happen throughout the world, that this is not as unusual as we would like it to be. So what we're seeing is there's a lot of energy demand that is rising, and sometimes that leads to outages that we could just see. The biggest driver for the rise of this energy demand is generally electrification, and that means all sorts of stuff. We just had a little video about EVs, but there's other things that are also being electrified. And the other big one is data centers that consume a lot of energy. The energy industry was used over the last 20, 30 years, 40 years to a relatively flat or very small growth energy consumption. You can see here the projections for North America. That's changing. In fact, the numbers that you see here are probably outdated again, because it feels to me like every day I look, there's a new projection that's pushing it further up. The problem is there's limits to how much infrastructure we can build. Supposedly, this is the biggest highway in the world. I don't know if that's true or not. It doesn't really matter. This is outside of Houston, 17 lanes each way. And I can tell you from my own experience, there's traffic jams on this highway during certain hours of the day, in days of the week. Now, for traffic, we're used to that. There's a jam every now and then during rush hour. On the energy grid, if there's a traffic jam, you have a power outage. That's essentially how this goes. So we need to figure out how can we deal with that limitation to the infrastructure that we have on the energy grid to accommodate the growth that's coming. What you see here after that outage that we had in Texas, ERCOT, our energy transmission operator, had to put out an app, and they have this app, and this was a screenshot actually from September in 2023. And you can see on the upper line, that's the energy generation that's available, and the lower line, that light blue line, is the consumption that is, or the load that is being projected. And for almost the entire day, there's really not any problems. Plenty of generation available, except in this case in the evening around 7 o'clock, these two get really, really, really close. That's the traffic jam, so to speak. And there were alerts going out, hey, if you can, reduce energy. Now, this is not a phenomenon unique to Texas. I had a conversation in Alberta last year, and they're telling me, oh yeah, we got those alerts too. I think this one was in January 13 or something like that. So this happens, unfortunately, way too often. The key to solving this problem is energy demand flexibility, or it's really about balancing the generation with whatever the grid can manage, meaning the poles and wires, with the load as well as with customers, their needs and we just talked about the prosumers, their ability to potentially contribute either with their own generation or contributing by reducing their own energy needs. And we talk about virtual power plants. We already had this term mentioned here a few times, VPPs, or distributed energy resource management systems, DERMS. And what they do is essentially they help either produce energy at certain times, reduce consumption at certain times, do load shifting of some sorts. The Department of Energy, and I have to apologize, sometimes I do have US references, and I know these days this is not a particularly well experienced thing here in Canada. Nonetheless, what they are referring to is they talk about load shifting, load shedding, load shaping, and shimmying. Now the first three is not necessarily as much of a requirement for artificial intelligence than the shimmying. But if you look into the shimmy, that's on a second basis type of stuff. Stuff is happening right now, I need to react, what can I do with that? So Schneider Electric plays in that space. We work, among a number of other things, with utility operators in the control room, and we have a management platform for the grid that is data-centric. What that means is we don't necessarily look at the process first, we look at the data first. Everything is centered on the data, and you see those three layers there at the bottom. I'm not going to go through all the details, but there's a data hub that essentially gets a bunch of different types of data sources, so the data is available once, and then you have an AI services hub right above it that consumes a bunch of the data and then processes a bunch of the data. And then you have all sorts of modules from grid planning to that DERMS piece to a distribution management system, et cetera, as well as a number of other third parties. Schneider Electric cannot do everything by ourselves. We do want to work with other parties. We need to integrate with other parties. So all of that is part of this platform that we have as a solution for utilities. And when you look at the far right, at the very bottom, there's some design principles. At the very bottom, it says AI where it makes sense. Now, what does that mean? AI where it makes sense means we don't really want AI to be in control, but we do want to leverage when and where it makes sense. And there's three primary buckets where we look at AI. The first one is a control room. The control room at a utility, for those who do not work in a utility, is essentially that's where the people are. They have like a gazillion screens in front of them with every portion of the grid visible to them to know exactly what's happening where. These are all of my sources, this is my load, this is the power flow, all of that. So in that control room, AI is of assistance to help them understand where is potential trouble, to then troubleshoot, and to really optimize and maximize the potential of the available resources that they have to manage that. We also use AI for planning. So not in the control room on the day-to-day, but what's going to happen next week, in the next month, in the next 2 months. We use AI for that. And then storm prediction, coming back to where I started. There is stuff that happens that is outside the norm, whether that is because there's a hurricane coming, whether that's because there's a snowstorm, whether that's because there's a wildfire. We use AI for some of that as well. I want to give a few examples as to what that looks like in real life and how we have deployed that with some utilities. You can see here, if you look at that graph, there's a red line that talks about some of the limits that you have. And this goes down to the feeder or the transformer level of the grid. And then you see a few green bars and you see a few blue bars. The green bars essentially indicate this is the potential to reduce load at a certain system level. The blue bars, this is a potential to potentially increase load. If I have a battery that could be charged, maybe there's a good time to do that. Maybe the grid really needs to actually consume more load. So that's what this is showing, and you see this flexibility and you can plan around that. And that takes into account essentially all the different grid resources that people may have even in their homes. A few examples. This one is with Pacific Gas and Electric. It's in Northern California, around San Francisco in the Bay Area. They are using this technology quite specifically for EV fast charging stations. So they have a lot of EVs, electric vehicles, in their territory, and they have a lot of fleets, and they want to have fast charging, and they want to charge semi-trucks, etc. Now, they don't have, PG&E does not have the system build out for some of those charging stations to support a fast charger at the time that they want. And so they're using essentially flexible contracts with those fast chargers to tell them, hey, you can charge them most of the time, whatever you want to do with your fast chargers, but there's times of the day when I don't want you to do that, or where I have to curtail you, or you only get 30, 50, whatever many percent. Are you cool with that? They are, and here's an example as to what that has done for them. One of their EV fleet customers gained access 18 months earlier to a fast charging site than they would have otherwise. And you can see what that does in terms of electrical fleet miles, etc. And PG&E was able to sell another 3,000 megawatt hours of electricity because of that fast charging station, otherwise they couldn't have used. Another case study is in the UK, Electricity Northwest. They really focus on this active network management. There's a real-time active network management, and there's a look at ahead active network management, and they use that to participate in the energy market. So they bid that into the market to essentially utilize whatever electricity is available, the cheapest one, to sell in the market. And what that has helped them do is defer capital investment and have a much more grid reliable and power quality and increase customer satisfaction. I do have to speed up here a little bit, so I'm going to go through this more quickly. Another case study, and this is basically taking us around the world. This is in South Australia Power Networks. What you can see on this one chart is they actually have so much solar on their rooftops that so residential rooftops, that they have more solar generation than they actually have power needs during many times of the day, which presents a completely different challenge for them. And they do the same thing, essentially get people, and that is individual rooftop homeowners, to agree to some sort of a flexible connection. Hey, you can put that solar on there, but I may not need all of the solar that your system is generating at certain times. If you're cool with that, I will pay you for whatever you can feed into my grid, but I won't pay you for anything else. And so based on that, they have been able to keep that grid steady. And this is the last case study. And I did want to have something in Canada, so I selected BC Hydro. And I also added Puget Sound Energy. Puget Sound Energy is in Washington State. BC Hydro is in British Columbia. They have very similar use cases. That's why I clubbed them together, and they're really neighboring each other. They work with C&I customers as well as with residential customers on all sorts of devices, from EVs, from thermostats, from water heaters, from batteries, to basically use all of them in a demand response program. So customers can enroll the devices, they get paid for that, and the grid is benefiting from that during peak season, as well as during some of the local constraints that they need to manage. So, closing out, using distributed energy resources offers a wide range of benefits for both customers as well as the utilities. On the left-hand side, it starts with more on the customer. There's community benefits, there's minimized costs, and that then moves over toward the utility in terms of resiliency, optimized infrastructure, and time to market. Some of these things are much, much quicker than building a new power plant. There's a couple of reports. One is from 2023. Another one is actually just from about a month ago that quantify some of those benefits. In 2023, the Brattle Group had published a report about the benefits of virtual power plants. Really, if you look at the net cost, and they were looking at, hey, what happens if you need resource adequacy, gas versus generation versus battery versus a virtual power plant, you see those net costs obviously being significantly lower. That requires artificial intelligence to really leverage that. And then the Forrester report is something that was just done literally last month. looking at some Schneider Electric customers and the benefits that they have received. And there's a report, I can share it with you. They basically had a payback on the investment within 16 months and an ROI of 184%. Thank you very much.